Hello everyone, and welcome back to Fluid Dynamics, Fluid Mechanics. Today we're going to be talking about Chapter 4, which is Fluid Kinematics, and we're going to cover the material in Section 4.1, but we're also going to spend a lot of time talking about some of the introductory concepts or reviewing some of the concepts about kinematics and about fluid flow that are introduced later in the chapter. So today's topic is actually, the math that we're going to do is taken from Section 4.1, but I'm also going to spend some time talking about some of the definitions and concepts that are introduced throughout the chapter. So we'll spend this vodcast and two more vodcasts, so 12, 13, and 14, we'll spend on Chapter 4, but we won't have to go over all of the definitions that we encounter in the rest of the chapter because we'll talk about them first. So one of the things I'm going to do today is on our presentation, I'm going to refer back to your textbook quite a bit. And the reason for that is there are some things that I want you to specifically know, and if you are able to find these ideas in your textbook, then you'll be able to go back to them when you need the definitions of certain properties. So, going to the document camera, which will come up in just a minute, we're going to start talking a little bit about fluid kinematics. And first of all, you may remember the term kinematics from either dynamics or possibly from Physics 1. But what kinematics is, it's separate from dynamics or kinetics, in that in kinematics we discuss the geometry of motion. We don't talk about the cause. Well, what is the cause of motion? The cause of motion is some sort of an unbalanced force, or the cause of an acceleration or a change in momentum is actually some sort of an unbalanced force. So when we talk about kinematics, we're only talking about what it looks like. So we talk about velocity, and we talk about acceleration, and we can also talk about position, which we can call position vector r, or we can call it x sub y, or something like that. But this idea that we're going to introduce in Chapter 4 of Fluid Kinematics, where we describe the motion, is very important, because when we talk about fluids, we have to look at fluids as being some sort of a field or a continuum. And basically, when we talk about a field representation, we talk about what the motion looks like, or what any property looks like. The property could be temperature or pressure, or it could be a variable of motion such as velocity. But any variable we look at, or let's just say property of a fluid, as a function of time and position, right? So if we wanted to write something like that in a mathematical manner, we could say that the property of the fluid is a function of position, x, y, z, and also time. Now, the specifics of that depend on the particular fluid regime. For example, let's talk about water flowing through a nozzle. Okay? This is like a hose, the end of your hose. Okay, so you're watering your garden. It's summertime right now, so I'm thinking about this sort of thing. And what happens is you have some particular velocity here, but as the velocity decreases, because mass flow rate has to be conserved, right? Because we can't change mass flow rate, and because the fluid is incompressible, we know that the velocity is actually going to have to be higher here than it is here. So the the velocity at the nozzle is greater than the velocity at the hose. That's a sub n and that's a sub h. And we know that the velocity is going to differ here. So if we were to take a look at a graph of velocity versus our location in the x direction, we would see that our velocity would be somewhat constant until we reached the beginning of the nozzle, and then it would increase to the end of the nozzle. So as the diameter there it decreases, the velocity increases. So this is one representation of a field, the velocity field. And in this case, we've kept it pretty simple. We have a one-dimensional velocity. It's just all x, and we're only talking about its relationship in the x direction. There'd be maybe something similar in the x and or the y and z direction, or maybe it would be significantly different. But basically, to think about this, if we were to extrapolate this into a three-dimensional representation, and I'm paging down in your textbook here on my computer screen, okay, and I'm going to show that to you. All right, so here we are in your textbook again, and you can see then that we let u, for our variables, equals the speed in the x direction. And remember, what is speed? Speed is the scalar portion of velocity. Velocity is a vector, so it has a magnitude and a direction. So little u is just its speed in the x direction, or the magnitude of the x component of the velocity. We can use little v is equal to the speed in the y direction. And we can also say that little w is equal to the speed in the z direction. Okay, so let me put that up on the document cam. Sorry, I meant to keep that on the doc cam. So if we let those three things occur, and we understand that each of these is going to be a function of position, x, y, z, and time, we could then write the velocity vector as u, which is a function of x, y, z, and time, times the unit vector in the I direction, or in the x direction, plus little v, not to be confused with capital V vector. This is also a function of x, y, z, and time, times the unit vector in the y direction, plus w, which is a function of x, y, z, and time, times the k unit vector. And I should put commas in between each of those. And this is called the velocity field. The vector v is the velocity field. What that means is that you can plot the velocity as a function of each of these things. Now that's a four-dimensional matrix or four-dimensional array, which is somewhat difficult to plot. So we generally simplify this. Now there's a lot of times where those functions can be simplified pretty significantly. And that's sort of the method of attack of using these field formulas. Where can we simplify? What can we eliminate? What is negligible? What isn't pertinent to the equation? So for example, some stuff doesn't change with time. If you looked, for example, at my hose with the nozzle, if you're squirting the same amount of water out of the hose over, let's say, 10 minutes, you're just standing there squirting the hose, there's no change in that flow regime over that period of time. Now, if you let off the water or you increase the water, then that would be different. But often it's not going to be a function of time. Also, maybe it's not important what's going on in the z direction or the y direction. Maybe it is. If you have an arc, if you're making an arc with the water, or if you're using an irrigation tube, those components of geometry are important and you have to take them into consideration. Also, of course, the fact that your pressure gradient with fluids operates in the z direction or in the vertical, whatever you call that particular direction. However, the method of attack to using these equations, because they get very complicated in a hurry, they had a lot of terms, one thing that you really would like to do is to eliminate the things that are not important in that particular case. So the velocity field equation that I just gave you is extremely general. So as your book will discuss with you, it says that the velocity then is a function of these four different variables, x, y, z, and t. So we can also say we know that speed, which is the magnitude of velocity, is going to be equal to those variables u squared plus v squared plus w squared if I take the square root of that. And that's just a three-dimensional version of the Pythagorean theorem. So we can find the magnitude of the velocity, which is the speed, relatively quickly using Pythagorean theorem. All right, now there are three other concepts that I would like to introduce at this time, which only one of them is really introduced in section 4.1. But these are ideas about how we examine fluids. We've talked a little bit about streamlines. We've not really talked about streak lines, and we've not really talked about path lines. But because fluid flows are very complicated, we try to isolate them and look at them in certain ways, or isolate certain types of properties, and then make a decision about what the fluid looks like based on sort of I would say an integrated or maybe just a ginned up version of those variables. But a definition of a streamline is in your textbook, and I was going to see if I could find the definition. I have a definition for streak line and a definition for path line. Okay, so on page 166 of your textbook, I'm going to flip you back to the podium PC so that you can see this, and go back to page 166. All right, and you'll see here at the bottom that a streamline is defined as a line that is everywhere tangent to the velocity field. A line that is everywhere tangent to the velocity field. And what that explicitly means is that if you were to draw a bunch of velocity vectors based on position, and then you drew the line that was tangent to them at all points, you would have something called a streamline. I was just seeing if there was a good picture of streamlines. There we go. All right. So basically, you know that a tangent, which is in this case v over u, right? Because we're talking about change in y over change in x. It's just a dy dx taken instantaneously. Then at every single location we can determine what those lines would be, right? Now, that's one way to analyze a fluid, and it's actually quite common. The other two are a little bit less common in terms of fluid analysis. But they do occur, and sometimes they are coincident with streamlines. But a streak line, which this is defined at the top of page 168 in your textbook, and a streak line consists of all particles in a flow that have previously passed through a common point. Okay, so it's all the particles in a flow that have previously passed through a common point. All the particles in a flow that have previously passed a given point. Okay. So in other words, when we're talking about streamlines, we're not talking about a particular particle at all, are we? We're talking about an area, or we're talking about an areal relationship. When we're talking about streak lines, on the other hand, we're talking about tagging, as it were, particular particles and then following them as they continue on their path, or through their, not necessarily their path, but on their journey throughout the fluid. So the last one, before I relate which these ones, how these relate and how they don't relate to each other, is a path line. And a path line is the line traced out by a given particle. A line traced out by a given particle. All right? So basically, if we have a line traced out by a given particle as it flows from one point to another, we've basically tagged a particle here. Now, one sort of a representation of this would be, if you think about, if you were a wildlife biologist and you were tagging elk in the thoroughfare. So most of you are aware that I am recording this from northwest rural Wyoming. We live about 70 miles from the border of Yellowstone Park. So Powell is over here. This is actually too far to the east, but I'll go ahead, I'll run with it. And this would be Yellowstone Park. And in between, there's a little town called Cody, and then the east entrance to Yellowstone Park at Pascatepe. And in between Yellowstone Park and Cody, Wyoming, is the North Fork of the Shoshone River, which is some of the most beautiful land in the United States, in my opinion. But also, it's a place, part of it is known as the Thoroughfare, which is a place where elk pass from one area to the other of the western United States. Now, you can use this idea of when wildlife biologists are looking at the behavior of elk, you can think about these in terms of streamlines, streak lines, and path lines. So let's take a look at the path line first of all. A path line, which is a line traced out by a given particle. What would that be like? A path line would be like tagging or putting a radio collar a single elk. An elk with a radio collar. Okay, so do wildlife biologists do this? Absolutely. So they find, let's call him Bruce. It's kind of an inside joke. Some of you may know what that is if you are from a ranching family. But we'll call our elk Bruce. And we put a radio collar on Bruce. And then as he leaves the thoroughfare, goes up into Yellowstone Park, comes back down into the thoroughfare, goes down into central Wyoming, and comes back to the thoroughfare over the course of a year, we can trace his path by tracing his radio collar. And that line that we would trace by following Bruce would be the path line. Okay, now a streak line is a little bit more complicated, but we can represent it the same way, where we have all the particles in a flow that have previously passed through a given point. All right, well, let's take our thoroughfare, and let's say that it's too large, so we're just taking a look at a single acre of the thoroughfare down here. So I'm going to blow this up a little bit. So this is an acre, which is quite a small amount of land, on the southeast corner of the thoroughfare. Okay, and we look at all of the elk that pass through that point. So we look at all of the particles, all of the elk that have previously passed through a given point. So instead of tagging one elk, we take a look at all of the elk that have happened to go through this particular point, and we watch what they do over the course of the year. So this is quite a bit more complicated, isn't it? Or it could be nothing. Maybe no elk passed through that corner. So our streak lines could be nothing, or our streak lines could be extremely complicated. And then let's talk about streamlines. Finally, A line that is everywhere tangent to the velocity field. All right, well, if we realize that we have, for example, x, let's say y and x, and we plot those points, and we look at the, well, I'm actually plotting the tangents, right? So we're talking about the actual movement, not of the elk, but of where the elk tend to go, I guess would be the best way to describe it. And the tangent is going to be dy dx, right? So there's, or if we were talking about a velocity, we could be talking about a du dt, dv dt, dw dt, depending on how many variables we wanted to study. So you can see then that the streamlines are tied to movement, streak lines are tied to an area, and a path line is tied to a particular particle. So this brings us to an idea that you may remember if you've had thermodynamics, is that sometimes we looked at a system and sometimes we looked at a control volume. And a system is a particular amount, not even an amount, but it's a particular mass, right? A control volume, on the other hand, is a particular place. So if we're looking at a particular mass, it doesn't even mean the same mass. It's not like a pipe. If we have a pipe and we have fluid flowing through the pipe, and we look at the pipe, that's a control volume, isn't it? Because we're looking at an area or a particular place, and we're watching mass as it moves through. So even if this always contains the same amount of mass, if we're looking at a place, it's not the same particles of mass. A system, on the other hand, would be like where we have a piston fitted into a cylinder, and then we increase the temperature or decrease the pressure, change the properties, and we observe what happens to this particular, these particular particles of substance. So even if the mass is the same, but if we're really looking at a volume or an area, it doesn't even have to be a consistent volume, the volume can change. But if we're looking at a place, then we're discussing a control volume, and if we're looking at particular mass, we're talking about a system. So in fluids, we look at fluids either one way or the other. We can't look at all of the mass and all of the places. It's just too complicated. So if we look at a particular place, even if that place changes size. For example, if you have a balloon, I'm not really very good at drawing balloons, but there we go. All right. And you put air into the balloon so it can inflate, deflate, the boundaries can change. That would be a control volume. The mass inside the system, then you look at the particular amounts of mass either entering or leaving the system. But this type of a view is more common in fluid analysis, and we refer to that as Eulerian. So when you're looking at a control volume or a particular place that a fluid moves through, then that is an Eulerian scheme of observing the fluid. If you tag particular particles, if you're looking at a particular mass, that is referred to as Lagrangian. And even though we've never really talked about it, when we work with solids, we're almost always talking about Lagrangian. If you're looking at a desk, you're looking at that particular mass, and then you move the desk around. Or if we tag an elk, and then we look at the movement of the elk, those two are both Lagrangian or system approaches. But control volume, we have a pipe, we have a flume, we have a cup that we pour water in and out of, we have a tub that we pour water into or out of. All of those things are Eulerian in nature and have more to do with the control volume than with a Lagrangian approach. Now, the other piece of information, if flow is steady, meaning if it's not changing over time. Streamlines, I wrote the wrong word, sorry, steady. Streamlines, streak lines, and path lines are all equal to each other. What I mean by steady is if there is no, steady flow is flow where there is no particular change over time. Steady flow means doesn't change over time. So, once again, garden hose, water squirting out, same amount of water, steady flow. There are some examples of flow that is periodic. It may not be truly steady, but you can approximate it over some period of time as being steady. For example, filling up a bathtub. If you have a tub, you put the stopper in the tub and you allow water to flow in from the faucet for some period of time, that flow is steady. But if you pull the stopper, or if you turn off the water coming in, or you change the volumetric flow rate of the water, it is no longer steady. So it's over some period of time, from the time you put in the stopper and turn on the faucet until you change one of those conditions, you can view that period of time as being steady. Another idea of this is there are types of flow that are just truly random. And one type of flow that's truly random is any sort of a turbulent flow. It's very hard to define turbulent flow. It's very hard to mathematically describe turbulent flow. So if you see, think about looking at maybe a body of water, like a lake. And if you watch the waves sort of lap up on the shore, you'll see that there's a periodic nature to the way that they lap if everything is pretty calm. So the wind affects the water, and the nature of what's underneath affects the water, and you may get like a flow where you see waves crash against the shore, little bitty waves crash at a very steady pace, one every 5 seconds or one every 12 seconds or something like that. Now, that's very different than a storm. So you get into a storm situation, and there's water swirling, and there's eddies occurring, and there's water breaking, and there's big crashes, and there's waves kind of like busting up on top of each other and creating breaks in the water and that sort of thing. That's a very random type of flow. Now, when we get into those types of truly random flows, we have to think about them a little bit differently, and we have to model them a little bit differently. It's a little beyond the scope of the class. We'll talk about it later. But what we'll talk about are steady flows and unsteady flows that can be approximated or simplified in some way. But we're really not going to talk too much about truly random flows. All right, so getting back to section 4.1 then, we've kind of discussed a lot of these ideas about one-dimensional flows, two-dimensional flows, describing fluids as a function of position and time. And we have also talked about some of the variable names plus some of the definitions that we'll need in order to sort of do this sort of analysis. So on our Moodle page, I've posted a homework set, and I would like to do sort of a representative problem of this homework set, which is problem 4.3 in your textbook. So I'm going to get to problem 4.3, and then I will work it for you to bring us to the end of this lecture. Okay. And it's still coming. Here we go. All right. Now, if we take a look then, there we go. I couldn't make it go. 4.3 at the bottom of the page. All right, there, I think you can see that. All right, problem 4.3 says that the velocity field of a given flow is given by v, the vector, is equal to 20y over x squared plus y squared to the 1/2 I. So what, okay, we'll talk about that in a minute. I'll just go ahead and write out the equation. Minus 20x over the same denominator, x squared plus y squared to the 1/2 j. And this is measured in feet per second. And it says this is where x and y are in feet. Determine the fluid speed, which is the magnitude of this velocity vector. Back over to the document camera. Okay, so I wrote down the equations here. The velocity is equal to 20y over the quantity x squared plus y squared to the 1/2 in the I direction, minus 20x over the same denominator in the j direction in feet per second, where x and y are measured in feet. So the question says, determine the fluid speed at points along the x-axis. Okay, so we want v as a function of x, right? And we want the angle between the velocity vector at some points between v and the x-axis at the points at point 50, 55, and 0, 5. All right. So that's a nice problem. And one of the things that you may think about is this is very geometrical and very tricky, isn't it? So in other words, we could draw this. We could draw v as a function of x and y, right? We could just plug in random points for x and y. And then we could make a determination about what the value is in terms of the vector, something I plus something j. And that would be a representation, a mathematical representation of our velocity at that point x and y. So this is definitely a field representation of velocity. It's definitely geometric. All right. I need to get some paper without scribbles on it. Here we go. All right, so first of all, if we go back to our original equation that was given in the textbook, we know that velocity field is u as a function of x, y, and z times I, or times the unit vector, plus v, the magnitude of velocity in the j direction, or the k direction, times the unit vector j. So in other words, that tells us that this quantity is u, and this quantity is little v. So let's use that as our starting point. Little u then is 20y over x squared plus y squared to the 1/2. And we're told that's in feet per second. Little v is negative 20x over x squared plus y squared to the 1/2. Right? And from this equation, we can surmise that w is equal to 0. In other words, the velocity in the z direction is not relevant. This is a two-dimensional flow. So how do we find the magnitude of the velocity, which is the speed? Well, we know that that's u squared plus v squared raised to the 1/2 power. And we have our values of u squared and v squared, or of u and v. So we can just plug in 20y over x squared plus y squared to the 1/2, quantity squared, right, plus negative 20y over the same thing, x squared plus y squared to the 1/2, quantity squared, and then we will take the square root of that quantity. All right. Well, if we square 20y, we get 400y squared. And if we square something that we're taking the square root of, then we can just 2 times 1/2 is 1, and that just becomes x squared plus y squared. Now similarly, we have here negative 20y squared. Negative times negative is positive, so that pops out as 400. I think I wrote the wrong variable. That should be x, right? X squared over x squared plus y squared. Okay, like that. And if you look at the 400, that's common to both of these, isn't it? So if I pull that out, I can write this as 400 times the quantity y squared plus x squared over the common denominator of x squared plus y squared. What happens here? Kind of convenient, isn't it? So we get that the magnitude of the velocity is square root of 400, which is 20 feet per second. Another interesting thing about this is not dependent on x and y, is it? So what that's telling me is that it is everywhere, at every x and y value, equal to 20 feet per second. So the velocity of the speed is constant. Excuse me, the velocity is not constant. The direction will definitely change because we have the variables in the vector equation, but the variables actually cancel themselves out in the speed equation. All right, so let's find out what is the angle of the velocity vector at 3 points. And the 3 points we're asked for are 5, 0, 5, 5, and 0, 5. All right, so first of all, let's find out what the velocity vector is. Let's call this A, B, and C. So at A, let's compute our velocity vector based on our original equation. We get that the velocity is equal to 20 times 0, which is 0 over, who cares, right? Because it's 0. If it's 0 over, as long as this is not 0, x squared plus y squared to the 1/2 is not equal to 0, I have a real number. So my velocity in the x direction, my u value at 5, 0 is equal to 0. Minus 20 times x, which is 5. 20 times 5 is 100 over x squared. 5 times 5 is 25 plus y squared, which is 0. Take the square root of that, and that's my component in the j direction. So my velocity at the first point, 5 and 0, is 0I minus, let's go ahead and do the math. The square root of 25 is 5, so it's 100 divided by 5, which is 20j. Okay, now there's a couple of points I want to make. If this is 0, this has to be 20, doesn't it? Because we already found out that the speed is everywhere equal to 20 feet per second. So that means that since it's just a two-dimensional flow, we have 0 and minus 20, and therefore we have to have minus 20. Now we can plot that vector, can't we? Because what we're asking is what's that angle with respect to the x-axis. So here's my point, 5 and 0. Here's my velocity, 0 and minus 20. What's that angle? Well, it's 90 degrees, or minus 90 degrees. Theta equals negative 90 degrees. Now you could have done that mathematically as well. Negative the tangent, or I would use tangent opposite over adjacent, but you'll come out with 90 because that value is equal to 1. Okay, let's do the same thing. I'm going to use the same graph again. I don't want to redraw my XY axis, but I'll go ahead and use my other 2 points. B, I want to know what it is at 5 and 5. So if I go back to my original equation, which is right here. I like to get everything on the screen. Okay, so I want to get my velocity here. My velocity at 5, 5 is going to be equal to 20 times 5 over 5 squared plus 5 squared, square root, and that is my I vector, or my U component, my X component of the vector, minus 20x, which is 20 times 5, over same denominator, 5 squared plus 5 squared to the 1/2, j. All right, now all I have to do is get my numbers. 20 times 5 is 100. 5 squared is 25. 25 plus 25 is 50. Square root of 50 is the square root of 25 times 2, which is 5 times the square root of 2, right? Okay. I. And same over here, I get minus 100 over, same thing, 5 square root of 2, j. So that's my velocity at 0.55. Right, so I'll plot that. First of all, square root of 2 is about 1.4, right? Let's just get an approximate answer for that. So I'll turn on my calculator, clear it, and I have square root of 2 multiply that by 5, take the reciprocal of that, and multiply it by 100. So that's about 14.14 I minus 14.14 j. Okay. All right. So when I plot that on my XY axis, well, I guess I do have to draw it again because, oh, there it is. I found it. Too many pieces of paper. Okay. So here at 5, 5, my velocity looks like 14.14 in the x direction minus 14.4 in the j direction. And so if I take, and of course the magnitude of that would be 20 feet per second, right? Because we've already decided that that is always going to be 20. Well, since my x and y components are the same, I know that this angle is 45 degrees, right? You could do the math once again. Just by graphing, I can see that. But it asks me what is the angle with the x-axis. So if I bring it down parallel, I see that it's actually negative 45 degrees. All right. And last but not least, we'll do problem C, which is at the point 0.05. All right, so going back to my original equation, we have the velocity is equal to 20 times y, which is 100, right? 20 times 5 is 100, over x squared, 25 squared, or 5 squared, sorry, plus 0 squared, square root. And then that's I minus, my original equation is that I would have negative 20x, so it's 0 over something. And once again, don't care what that is, because as long as it is as long as this is not 0 or something else like the square root of a negative number, then we're golden, and it's not. So it's a non-zero number. So that tells me then that my velocity at that point is just 100 over 20, square root of 25, which is 100 over 5, which is 20, and it's all in the I direction, which once again makes sense because we know that the magnitude of my velocity has to be 20. All right, so what that means is that at that point, 0, 5, which would be right here, more or less, that my velocity is purely x, and it has a magnitude of 20 feet per second. What's my angle with the x-axis? The angle is 0 because it's parallel. Theta equals 0 degrees. All right. All right, ladies and gentlemen, so that concludes our discussion of section 4.1 on velocity fields. And we've also spent some time talking about some of the variables and some of the meanings of different definitions that we will use in the rest of the chapter. So when we come back for Vodcast 13, I'll do section 4.2, but we'll sort of start with an understanding of Lagrangian, Eulerian, streamline, streakline, pathline, steady, unsteady, periodic, steady, truly random, and that sort of thing. So we'll see you for 13.